He says this is also called the Hilbert adjoint, and so but yes, this is if we look at the context of if A is from, let's say, Cn to Cn, and you have this condition that Ax, good grief, Ax comma y is equal to x A conjugate y, like that. Well, by definition of the inner product on Cn, we're talking about what? We're talking about Ax transpose times y, right? Conjugate is equal to x transpose A star y conjugate. But that gives me x transpose A transpose y conjugate is x transpose A star conjugate y conjugate, which then implies that A transpose is equal to A star conjugate, which implies then that A star is A transpose conjugate, which of course you will recognize as the Hermitian. That's a dagger in physics, right? Yeah. So yeah, the Hermitian adjoint is the, well, it's the Hermitian adjoint. So it's the conjugate transpose in the context, if you want to think of it as a matrix. So his first theorem is that the adjoint operator of a bounded operator is bounded. So how did you, so basically the norm of A is equal to the norm of, so I think that the norm of A was the supremum over the norm of x equals to 1 of the norm of Ax, wasn't it? That was our definition of the operator norm. We take the supremum of the values of the operator as it sorts through things of unit length in the Hilbert space. But so the thing is that the norm of Ax is the the square root of the inner product of Ax with Ax, right? And well,
Can't we
yeah.
automatically calculate versus star?
I mean, I could do this. This is the square root of inner product of x with A conjugate Ax. I mean, that's true, but
They're saying that.
what happens if I do this? Just a second here. I mean, well, this is equal to A star x, going the other way with the definition. And so this is equal to the square root of the conjugate of which is equal to the square root of right, because I have that right here and I've still got my conjugate, right? But you can undo the conjugate, of course, because it's the same stupid thing on both sides, and then that is, so basically this is the same as the supremum of the norm of x equal to 1 of the norm of a star x, which then proves that, of course, but that is by definition the norm of the adjoint. So if they're bounded, they're equal. And in fact, he also points out that if you calculate similarly, if you calculate, you can also show that the norm of a star a is equal to the norm of a squared through similar calculations. So then, well, I think that's a good place to start, more or less a good place to stop. We'll continue on in this adjoint operators section next time. Like the next thing we do is define self-adjoint, which is sort of the complex analog of symmetric. And because, of course, the adjoint is the transpose in the real case, and in this context, and then he gives some examples of like Fredholm operator and a couple of different examples of how the adjoint works in these contexts, and for our favorite Hilbert Space examples, and then he shows how we can decompose a bounded operator in terms of a self-adjoint and self-adjoint operator and a well, what's the word? I'm listening for the word. He's got some kind of like real imaginary breakdown of things going on, and if you look ahead here into like theorem 4.13, he's unique self-adjoint operators A and B such that T is A plus IB and T star is A minus IB. So it's kind of a operator analog of like real and imaginary parts. All right, so there's that. And then just to take a look ahead briefly, section 4.5 is on normal, isometric, and unitary operators, which I'll try to summarize the high points there. Positive operator section, I think we're going to skip. I don't think that matters too much to us. Basically, the positive operators section, it is, in linear algebra, you can study the question, what's the square root of a matrix? In some sense, that whole section is studying the question, what's the square root of an operator? When does that even make sense? And it gives a pretty general answer to that. Section 4.7 matters more because it's on projection operators, and projection operators are important to understand for interesting things. The compact operators section, what I'm trying to do is to look ahead into the Hilbert Space section and see I'm trying to think about what sections I can skip and not hurt the course too much. Of course, we need to cover section 4.9 on eigenvalues and eigenvectors. There's some really interesting departures from the finite dimensional case. In particular, you can't take the determinant of an operator in infinite dimensional space. So how do you talk about the degeneracy? Because that's essentially and then the spectral decomposition, of course, is interesting. So I will try to get us through these things in not too long. And then hopefully, I think either in the midst of that, or right after it, I'll try to do the separation of variables, like boundary value problems in differential equations, because I told you guys I wanted to show you that. And anyway, I think that's it for today. So thanks.